Hi everyone, today I'm going to show you the process of how I build a machine learning model to predict whether to approve the credit card application. After loading the data, I conducted exploratory data analysis. I started by checking for missing values to make sure the dataset was clean and complete. Then I analyzed the numerical and categorical features to understand their distributions and general patterns. Next, I look at the distribution of the target variable and find that the class with target equals to 1 represented only 13% of the dataset, which indicates a severe class imbalance. To handle this problem, I use Smooth during the model development progress to generate synthetic samples for the minority class and improve class balance. And for the matrix selection, I mainly use the ROC AUC because the dataset is imbalanced, with only 13% positive cases. In this situation, accuracy can be misleading because the model can get high accuracy by mostly predicting the majority class, but but ROC-AUC is more suitable because it measures how well the model separates the two classes across all thresholds, so it gives a more reliable evaluation of performance. The first model I built was the XGBoost model. I used random search CV to tune the hyperparameters and identify the best performing configuration. The best parameter set, including a learning rate of 0.01, a maximum depth of 12,700 estimators, and a subsample ratio of zero point 0.6, among others. During cross-validation, the best XGBoost model achieved a ROC-AUC score of 0.95, which initially suggested very strong classification performance. However, when I evaluated the two models on the original unresampled test set, the AUC dropped significantly to 0.55. The large gap between the cross-validation AUC is the test AUC indicates that the model did not generalize well to unseen data. In other words, although the model performed very well on the resampled training data, its ability to distinguish between the positive and negative classes on the original imbalanced test set was only slightly better than random guessing. Next, I developed a LightGBM model and again used randomized search CV to optimize the hyperparameters. After tuning, I evaluated the model on the original unresampled test set. Compared with XGBoost, LightGBM achieved better predictive performance with a higher AUC score. This result is this result is important because AUC is a more reliable metric than accuracy for highly imbalanced classification problems. A higher AUC means that LightGBM was better at distinguish between the minority and majority classes across different classification thresholds. Therefore, LightGBM demonstrates stronger regularization ability and was a more effective model for this task. Then I use learning curves to compare model performance on small resample data and on the original scale training data. In both cases, the training AUC stayed close to 1, which means the model fits the training data extremely well. On the small resample data, the cross-validation AUC increased substantially and reached around 0.95, indicating strong validation performance after resampling. However, on the original scale training data, the cross-validation AUC remained much lower, around 0.51 to 0.55, which only slight improvement as the sample size increased. This large gap between training and validation performance on the original data suggests clear overfitting. It also shows that the model performed well on the resample data, but did not generalize well to the original imbalanced data distribution. The analysis correctly identifies overfitting. The model shows a near perform training score and a high cross validation AUC on small resample data. But the test AUC on the original unresampled test set is only 0.5564. This large performance gap indicates that the model does not generalize well to unseen real data. The learning curve also shows a large gap between training and validation scores on the original data, which is a clear sign of overfitting rather than underfitting or good generalization. For the fairness evaluation, I use gender as the sensitive attribute and assess the model using several fairness metrics, including demographic parity difference, equal opportunity difference, predictive equality difference, and average absolute odds difference. For all of these metrics, value closer to zero indicate better fairness. Before adjustment, the model shows a demographic parity difference of about negative 0.0022, an equal opportunity difference of 0.0255. Overall, these values were already relatively close to zero, suggesting that the model had reasonably good fairness performance. To further improve fairness, I adjusted the decision threshold for the unprivileged group. The original true positive rate for the privileged group was about 0.054, and the optimal threshold for the unprivileged group was tuned to 0.40. In order to reduce the equal opportunity difference, after threshold adjustment, the equal the equal opportunity difference improves significantly from 0.0255 to 0.0017, which means the recall gap between the two groups become more smaller. This shows that improving one fairness metric may lead to trade-off in others. Overall, the adjustment successfully improved fairness in terms of equal opportunity, while maintaining relatively small disparities across the other fairness metrics. To interpret the model, I use sharp global explanations. This summary plot ranks features by importance based on their average absolute Sharpe values. The most important features are total income, account length, own property, and age, which means these variables has the strongest impact on the model's predictions. In the plot, each dot represents one sample. Points on the right increase the predictions for the positive class, while points on the left decrease it. Red indicates higher feature values and blue indicates lower feature values. From the result, higher total income and longer account lengths generally push the model towards the positive prediction. Also, gender is included in the model, but it is not one of the most influential features. This suggests that the model relies more on financial and behavior variables than on gender, which is consistent with the fairness analysis. Then I also have the Sharpe local explanation. This Sharpe force plot provides a local explanation for one individual prediction. The base value is the model's average prediction across the dataset, and the final value, fx, is the prediction for the specific case. Red features push the prediction higher towards the positive class, while blue features push it lower towards the negative class. In this example, although features like years employed and age increase the prediction, the combined negative impact of features such as own property, occupation type 3, number of children, and account length is stronger. Therefore, the final prediction is pushed below the baseline, and the model classifies its instance into the negative class. While the model is not strong enough to fully automate approvals, it still has business values as a decision support tool. Its role is not to replace underwriting judgment, but to improve prioritization and consistency. For example, it can help fast-track clearly low-risk applications, flag higher risks or borderline cases for manual review, and reduce unnecessary workload for our approval teams. Even with moderate predictive power, that can still improve efficiency, reduce avoidable errors, and create a more scalable approval process when combined with human oversight.